Okay, so today we're doing two variable statistics. The first thing we look at is the scatter plot. So the scatter plot has the x and y axis like most graphs do. The x is going to be your explanatory variables and your y is going to be your response variables. So what you're going to do is you're going to plot each point in your data set and you look at three things. You look at the direction, the shape, and the strength. So the direction could be either positive or negative. Your shape could be linear, exponential, and so on. And your strength could be either very strong, moderately strong, or weak. So let's look at something like this. So in this case, you have all these points lined up. You see, you have a very strong relationship. The points are clearly positive, they're going in the positive direction. Over here, you have a very weak relationship. The points are not lined up in the same way, but you can still tell that it is positive. So that brings me to my next point, the correlation coefficient. That's your R. So that measures the strength between your two variables, your x and your y. So in a instance when you have a very strong correlation, you're gonna have either 1 or -1. -1 means it's very strong negatively, and 1 means it's very strong positively, and 0 means there is no actual relationship you see there. So in an instance like this, it's not going to be 0, but it's going to be very close because you can barely see any relationship at all. In this case, it's going to be 1, it's very positive, so it has a positive value, and it's almost perfectly correlated. So let's go next to the least square regression line. The least square regression line is, out of all the possible linear fits, the least square regression line is the one that has the smallest possible value for the sum of the squares of the residuals. So basically, in order to find a residual, you have to look at the equation of the least square regression line. So you have y hat, not y, Mr. Holmes, equals a plus bx. So b is going to be your slope, a is going to be your intercept, and what you're going to do is you're going to plug in your x value that you see in your graph. You're going to get a predicted value. The difference between the predicted value and the observed value is your residual. Your residual line basically minimizes that difference between what you see and what you actually calculate, and that's why you have this line. It is the best fit. Moving on, let's go to r squared, which is the coefficient of determination, which is basically just your coefficient correlation squared. So what this does is it gives the proportion of the variance of one variable that's predictable from the other variable. So let's say you have something like this. Let's say r squared is equal to, I don't know, 0.85. So in this case, you have an 85%. What it tells you is 85% of the variation in your response variable is explained by the variation in your explanatory variables. However, it also tells you that 15% of the data is left unexplained. This is very important because it tells you how much of the data is best represented by the line. So if you could have a very high value for r squared, the line clearly works. However, there's another way to tell if the line doesn't work. That brings me to my final point, the residual plot. So the residual plot on the y-axis has your residuals, and on the x has the original x values or the explanatory variables. So what happens if you have no pattern in the residual plot, then the line does fit. However, if you do have a pattern, let's say a u like a parabola or a v like an absolute value graph, if there is a pattern, then it means that this least square regression line is not a good fit and not an appropriate model. You have to use a different shape. Thank you. Come again.